Okay, so today we're gonna try to finish off this nearest neighbor, fast nearest neighbor calculation stuff. So like I said last time, this is a little bit detailed kind of stuff. There are some interesting details and perhaps some less interesting details. But I do want to get across the message that there are interesting things you can do in this to speed things up, potentially at least. Okay, just to remind you what we were doing, we were looking at metric distances, okay, for the first part, and we're going to be using often this, for example, this squared, this Euclidean distance, the square root of the squared distance between x and y is a metric. Note, by the way, that the square of this, x minus y squared, is not a metric. Okay, so that's you do need the square root for this first part. And we can prove that this way. So I apologise for having my lunch. Okay, so remember a metric is positive or negative, and it's got this requirement that the distance between these two things is bounded from above by this plus this. So this is kind of like triangle inequality, that it's shorter to go from x to y than it is from x to z, and then from z to y. Okay. And the question was, could we use this inequality in some way to speed up calculations in nearest neighbours? And one result we can use is this result: if the distance between x and y is half the distance between z and y, then we know we don't have to compute the distance between x and z, because we know that it must be smaller. So the distance between x and y must be smaller than the distance between x and z. Okay, so I tried to give you a geometric picture of this last time, and maybe this is a slightly. I think these slides have been updated, by the way, actually, from the ones which were there last week, and the corresponding PDF I uploaded this different as well. So do make sure you get the latest version. So the geometric picture is these are xi and xj. So these are two data points in your data set, and Q is your query point, and you want to find which is the closest x in your data set. So let's imagine you've already computed distance between query and xi. So we've pre-computed, we assume, all of these pair inter data point distances, the distance between xi and xj, and you store that in some big matrix. So we call, say, dij is the distance between xi and xj. So the basic point is that if you know that this distance here is less than half of this distance here, then there's no way that Q can be closer to xj than it is to xi. So depending on your abilities to visualize Euclidean geometry, you may see this better than I do, but I think it's fairly clear. At this point here, this is the midway point between xi and xj. So you could imagine an extreme case. So if this Q, this is the distance between xi and xj, were over here, okay, then even if you were to sort of say, well, take a distance over here away, there's no way that point there from there to that distance from there to there must still be smaller than this distance from here to here. Okay, so basically, as long as you're within this hypersphere bounded halfway between this distance, you must always be closer to xi than you are to xj. So the worst case scenario is when we put basically a Q along this distance here. So at this point here, if you think about it, if Q were there, basically it could be equidistant between xi and xj. If Q were over here, though, actually it must be closer to xj than it is to xi. Right. But I don't know if it's down here, it cannot be. So. Okay, so this led us on to Orchard's algorithm, which, I don't know if you remember this, but the idea is that you first compute all of these pairwise distances, and then you use those to construct various lists. Okay, so for each data point xi, you construct a list of the other data points which are closest to it in increasing order. So that would mean that in this case here, so the list for the ith variable, the ji1, that means that the distance between xi and xj1 is less than the distance between xi and xj2, the second one in the list, etc. So you just store here the indices of these vectors, which are closest to pi, in increasing order. Okay, so it's a lot to store because you have to do this for every data point. Okay, so every training data point, you've got a corresponding n minus 1 list. N is the number of points in the training set. Okay, so what do? You first of all, you guess a vector xi is your potential nearest neighbor. And you compute this distance dq between q and xi. And then you could do the following thing. You say, well, look, let me check. I go to the, first of all, I jump to the list corresponding to xi, to the li, and I check the distance. I first of all check di and the first element of this list. Okay, so that's d between xi and xji subscript 1. Okay, and if this distance here is less than half of that distance, then we know that the first element of this list, vector corresponding to that, cannot be closer to the q than the xi itself. Right? And because this list is sorted, that means that none of the others in that list can be closer either. So you're done. You've already found the nearest neighbor. Okay. If this is not true, then what you need to do is you need to move on and actually compute the distance. You consider, the first one in the list now is a potential new candidate. So you say, well, I'll compute now the distance between q and xji1, the first element of this list. So if this distance here is better than what you've had before, your current best distance, then basically this becomes your new best guess. So that means that xji1 was potentially a better candidate than what you had before. And now you jump to that list for that new candidate. Okay, so you jump, so let's say the first one, I don't know, let's say it was element vector number 3 or something like that in your training data set. And you find out that, say, the first element, say, is ji1 is, say, 3. And you find out the distance between q and that element is less than the distance between q and xi, you jump to the list number 3, and you repeat this process, checking whether or not the first element is less than half the distance. Okay, and that's it, basically. So what you'll do is you'll go along, you'll jump to a list, you keep going along this list. And if this is not a better, by the way, if this were not true, if this element were not better in this list, this distance, you just keep going along the list until you find either an element which is better and jump to its corresponding list, start, or you go to the end of its list, in which case you examine all of the potential nearest neighbors and you're done. Okay, this is kind of like it's called a list traversal algorithm. You're traversing lists, jumping. Is it clear? Should be. It's maybe I think these things are easier to understand once you've tried to program it. But there's a big computation cost both in time and storage at the beginning. So for Euclidean distances, it's going to d is the dimension of the vectors. Then it's going to cause you, order d n squared calculations. And you've got to, also go along with Ochi's algorithm. You've got to actually, at each point, compute then the members of this distance between q and a member of the list. But that's just an order d operation in the Euclidean case. So what you're hoping is that the geometry is such that as you're going along, you don't need to examine many list members, in other words, the many data points, and hopefully you'll crash out of this algorithm and say, I'm done, basically. There's no way anything can be faster. So that's bad. The order n squared storage is bad. But it's good in the sense that there's nothing really, you can rattle through with the Ochi algorithm. You don't need to do any. Once I give you a new query and you've done all this pre-computation, you don't need to do any order n operation. Basically, you can just start to try to find the nearest neighbor, and if you're lucky, it'll be very fast. Okay. So this is another algorithm called approximating and eliminating algorithm, search algorithm. And in this case, we're going to bound the distances another way. So we're going to say the distance of q and xi is bigger than this. So where does this come from? It's from the triangle inequality, because if we add this to the left-hand side, that's just saying nothing more than the triangle inequality. So I think this is where we got to last time. So if we define, say, a set of indices I for which you've already computed the distance between q and elements of that list, I, then we could say, well, this is true for, we've already computed this distance for each element I of the list. So what we could do is we would like to find the best bound. So the best bound in this case would be the one which is as high as possible. So we want to sort of say, the distances from q to those data points are all bigger than some number. We want to make that number as big as we can, to bound them as far away as possible from the current point, okay? So what we can do then is we can maximize over all the elements of this set for which you've already computed those distances. Okay, so just bear in mind that this here you've already computed. This is a pre-computed thing. This is you're looking at the ijth element of your distance matrix. These you've already computed. This is the ith element of your vector of already computed distances. So you just need to run. This is just this is the difference of two real values. So that's fast to do, and you need to do the max over all the number of elements of this thing. But then you have to do that for every j which is left. So you have to do this n times in the beginning. Okay. So the bad thing about this is that this will require at least one order n computation to calculate all of these bounds, basically. But there are a limited number of distance calculations here. So these kind of things are, it's difficult to say which is the best thing to do, because it depends on how expensive it is, whether or not you are really killed by the distance calculation, or if n is killing you, right? There's just a number of training points in your data set. So it's hard to say which is, in your practical situation, which would be preferable. Okay, so the idea then, maybe I can show you the picture. So you come along, you have to calculate all these lower bounds. So you know that the distance between, the optimal distance is greater than all of these lower bound values. So they're all up there somewhere. And you come along now with the data point, and you say, well, I compute the distance between q and some candidate. Let's call it x star. Well, if this candidate here is so if you're looking for the lowest distance, okay. So if you know that the distance between q and x2 is bigger than that value, it's up there somewhere, and you've already got one which is here, right? Then there's no way L2 and x2 and x3 in this case could be better candidates than x star. So you can eliminate them. So when you're looking for the lowest, the nearest neighbor, so you're looking for the smallest d. So if you know that L2 is already bigger than some d, then there's no point going to L2 or L3 in this case. You can eliminate them. Yeah. Okay, so the idea about ESA then is that you have to eliminate, after eliminating them, you only need to concentrate on the remaining data points here. And you can use this, you don't know the distance actually from Q to these data points. If you knew that, you'd be done. So what you do is you say, well, actually, I'll use these lower bound distances as kind of surrogates for the unknown true distance. And I'll use them to rank which data points I search for next. So in other words, I could say, in this case, L5, X5 would be a good candidate to go for, because that seems to have the lowest possible value. I mean, you don't know the true distance; it could be anywhere in here, but it's not an unreasonable thing to guess that X5 might be the best thing to do. And then, in this case, X4 would be the next one, and X1 after that. So there are different variants of this algorithm. So if you tried then x5, the next point, you could say, well, now I've computed x5, the distance between q and x5, and I can include that in the set I of examined data points. Okay? And then that will get another bounding. I get another set of bounds, and I rerun this elimination algorithm. Okay. In other cases, people might say, well, I don't want to keep increasing this set I every time. That's going to cost me too much in terms of operations to get the best bounds. Maybe I'll just stick with the current bounds I've got and just keep going. So the worst case what you could do is just say, well, I'll just do it. I'll just do it once. I'll just do one optimization. I'll get these bounds. Try to get rid of some data points, and then just use that one bound to reorder the data points, and I'll just then go through them sequentially, hoping that I will find a better optimal this way. Okay, so similarly to the orchard algorithm, we are assuming here that we've got access to this distance matrix. Okay, so that's expensive to compute. Also evaluating this bound for if you've got m remaining data points. Well, you're going to have an m here, and this is going to be the number of data points that you've already computed the bound for. So this is going to correspond to the max operations here. So this is quite expensive in principle. So you might in principle consider variants which don't maybe increase this, perhaps try to keep that fixed in some way. And then similar to the orchard algorithm, you hope that at the points you will just have eliminated all other, you've eliminated so many points that you're just left with one, basically. So a unique point left. Okay, so I'll show you the demos of this later. But there's an obvious problem here, which is that it's going to be in general expensive to store this distance matrix. So if you've got 10 million data points, you don't really want to be storing this 10 million by 10 million matrix of distances. So what can you do? There are various things you could do. One of them I like to call using buoys. It's got different names. Some people call them pivots, basis vectors. I don't know. But I'm going to use this terminology. And these buoys are some vectors, and there are a small number of them. Okay, and you are free to choose these points. They could be data points from the original data sets, or they could be points that you like for some reason. Okay, you're free to choose them in any way that you like. I guess there are smarter ways to choose them than others, but let's imagine you've got these guys. And what we're going to try to do is to use the distance between xi and each of these buoys, so remember a small number of them, to kind of, as an approximation in some way to our distance between xi and xj. So I'm only going to compute the distance between xi and bj, and that will, instead of being an n squared matrix, it'll be an n by b matrix. Okay, where b is small. So I'll go down to, from b is 6, and I'll go down to sort of certain linear storage rather than quadratic storage. Okay, so how do we use this? So there's two things we can do. So if you've been following this fairly carefully, let's look at the first equation. So this is a similar lower bound to what we had before. Okay. So just to see that, forget about the max for a moment. Then we've got dq to xn plus dbm xn is bigger than dq to bm. So one way to think about these things, like I said last time, is that you've got a dqxn here, and on the left you'd have dxn and bm symmetric. So essentially those xn's are the same. You can collapse them into the bound on the remaining variables. That's one way to think about it. Okay. So again, we can, because we've got a collection of these, one for each buoy, we can then get the best lower bound by maxing over the boys. Okay, so that's going to take a order B operation here. We've already pre-computed this. We have to compute B of these. These were already computed. So for our query, we'll have to calculate capital B distances from the query to each of the boys. Okay, so rather than computing the distance from the query to every data point in xi, okay, we're just computing the distance from the query to every one of these small number of boys. So we're doing the B distance calculations to start with. Okay. Similarly, we can get an upper bound by triangle inequality, which is given by this. This one in this case is just purely the triangle inequality, and then we want to find the best upper bound, so we'll minimize that this time. So we get these two lower and upper bounds, and I'll put a tilde on this one just to try to distinguish this between this and the lower bound from the ISA algorithm. Because remember, the lower bound in the ISA algorithm is not using the boys; it's using the actual data points themselves. Okay, so there's a slight difference. So ln tilde is not the same necessarily as ln. There's different lower bounds. Okay, so now let's imagine that you've done this and you find some lower bound which is bigger than some upper bound. Then basically this means that this lower bound here, this m, can be eliminated. So let me just see that as a picture. So here are some lower and upper bounds for your distances. So you've got some query and you've computed this. Okay, you've chosen some boys and you've computed these corresponding lower and upper bounds. So what it's saying is, look, well, you know the distance between the query and x1 is somewhere, it's definitely within here. It can't be anywhere else. Right? You don't know where it is, but it's in here somewhere. And similarly, the distance between q and x2 is somewhere in here, and similarly for the other ones. Okay. So if you look at this one here, well, look, the distance between q and x1 is at most this value here. The distance between q and x2 is at least that value there. That value there is higher than this value. So there's no point considering this x2. It cannot possibly have a distance smaller than x1. And similarly for x3. These remaining ones, though, you don't know what's going on with them, right? So you could be that you're unlucky somehow. It would seem to suggest that probably this one would be a good candidate to go for, but you never know. It could actually be in here, so you cannot completely eliminate that. Okay, so that's the idea, and we can do a similar thing as with the ISA. I mean, pretty much it's the same, really. The only thing that we're going to do is, so you saw how the elimination's working there. And all that we're doing is we're replacing those distance calculations before, those bounds, with these bounds which are coming from the boys, rather than using all of the data points. Okay, and we just rerun these out. So it's the same idea. Okay. So these are, in this case, the bounds which are left after doing an elimination. And one thing that you can do then is to reorder or to resort the data points, say by lowest bound value first. Okay, so this one, this one, this one. So I call them, after relabeling or reordering the data points, the remaining data points. So then you might say, well, I'll start with this one, and I'll check whether or not what is the real distance between q and x1. And if that real distance is, say, here, right, like in ISA, you know then, because L2 and L3 start above that value, there's no way that these guys can possibly be closer than x1 in this case. and you're done. The algorithm terminates. If not, then you move on to the next one. Then it's up to you whether or not you want to say, in principle, you could say, so I've computed now the distance between Q and X1, and I could actually incorporate that in my, get an improved bound. That's also possible. Or you could just say, I won't bother recomputing the bounds, I'll just stick with this existing bounds, and I'll just use them. I keep going along. Now I'm going to compute this. If this were, if the distance between Q and X1 were, say, here, right, then you would have to consider X2, right? And then, so now it's like you're in the same position as before. You say, well, that's my new best value here, and I consider now whether or not L2, the real distance here, and you keep going like this. It's a bit hard to show because there's not much difference between these two, but it's the same idea as before. Is it kind of clear? It's a bit complicated, this stuff, but you can look at the code actually if you want. The MATLAB code is all it's available. I don't think I put it on the Moodle page, but I'll put it on there today or tomorrow perhaps. Okay, so that's that. And sorry, this algorithm is called linear ISA. I guess because it's linear storage for a fixed number of boys, it's kind of linear storage. The bad thing about it though is you've got this sort of order n operation to compute all these lower bounds, okay, which is potentially expensive. Very big now. You can also think about doing the orchard with the boys, but I believe that this is not useful actually. And if you want to read the PDF about that, I try to explain why I think that's not useful. I believe that the ISA, the linear ISA, dominates the orchard with boys algorithm. But feel free to take a look. And so here's an example. So this is with some pre-elimination, as I call it. So the dots are, you can't see them very well, but these are data points. Yeah, so these blue dots are data points, and there's also a blue dot for where there's every cross as well. Okay, so there's 30-something data points here. And our query point is here. And these blue circles these are boys. In this case, the boys just happen to have been chosen to be subsets of the randomly chosen subsets of the original data points. But you could place them anywhere that you like, really. So remember what's going on now is that the distance between X and all the boys will have been pre-computed. And we'll do that for all of the data points. Okay, so we'll have some matrix there. Then I can compute, based upon that, these lower and upper bounds. Okay, based upon my distance from my query, based upon that upper and lower bound tildes, I can then eliminate immediately some data points. And in this case, all the red crosses are points which can be eliminated from that initial pre-elimination stage. Remember where we had this situation, pre-elimination situation here. So then I immediately get rid of all those points, and I'm just left with these points here. 3 points in this case, and 4 points actually, sorry, 1, 2, 3, 4. And I then ran some algorithm, I can't remember which one now, to find the nearest neighbor. You could use ISA or whatever you wish, really. Okay, or this linear ISA. But I think the point here is the big win in this particular case is the pre-elimination. It's getting rid of a huge number of data points. Okay, so you don't have to do at most 1, 2, 3, 4 high-dimensional distance calculations. Although, bear in mind, again, to do this pre-elimination, you have to do we have to run this bound, the catalog bound, for all of the n data points. So that's really expensive. Okay, so I don't know if it's particularly instructive to show you this, but we can have a look. So here's another. Just another random set. Okay. Okay, so it claims here that this particular case, yeah, I mean, these are both a little bit weird actually because they're both in the corner, but you know, you can eliminate all of these data points and just consider these ones here. So there are 100 data points, so the naive method would require 100 distance calculations. So the naive method, of course, is just computing the distance between the query and each of the 100 data points individually, just sorting them, using some sorting algorithm, and picking the lowest. So Orchard's method here requires 21. When I say distance calculation, I mean high dimensional distance calculation. It's two dimensional here, but I mean Euclidean distance calculations in this case. Orchard's method, 21. ESA method requires only 6 calculations. That's not using pre-elimination. That's just the pure ESA and Orchard methods. Okay. These ones down here are using the Boys to do the pre-elimination. So using 10 Boys in this case, we got rid of all but 8 candidates. Apparently, the ones in the right corner, I guess. And then the Orchard method with Boys, which I didn't describe, takes 17 distance calculations. The linear ESA with these Boys takes 16 distance calculations. So yeah, I mean, it's hard to, really say which is better than this. It really depends upon what application you've got. But you can see there is obviously some advantage to be had. Okay, so that's that. Okay, that's triangular inequalities, and there are many other many variations on these things, which I don't know about. But you can use these things. People have made use of them not just for nearest, neighbor classification methods, but say for, k-means clustering, for example. There you also have to find the nearest neighbor, and there are smart ways to use the fact that at the previous iteration you'd already done some calculations to, when you do k-means, because it's an iterative algorithm, right? And then at each iteration, you can use the fact that you've completed some distances in the previous iteration, carry them across the next iteration, and eliminate a lot of very long calculations. There's a nice paper on that. It came out at ICML 6, 7, 8 years ago. But anyway, the point a little bit is that that's all very nice, but it's still quite expensive. I mean, you kind of got this order n calculations, or you've got this order n squared storage. So that's nice, but it's maybe there are other things you can do. So here's something else called a KD tree. Did you do this elsewhere? Oh, okay, so that's good. So k-dimensional trees. K is actually going to be D in this case. I use D rather than K, so it's really D-dimensional trees rather than K-dimensional trees. And a KD tree is a kind of what they call a spatial data structure. In this case, it's kind of a hierarchical partition of the input space. And we don't have to store much. The storage is very cheap, and basically there are no obvious order n operations required, except in some worst case. So that's kind of good. We're going to do the gyration based upon the squared Euclidean distance. There may be other distances for which it's also doable, but I'm just going to concentrate on this one. So there's nothing to do with metrics now. Okay, so we're going to forget about metric distances. We're actually going to use a non-metric distance here, a squared Euclidean distance. Okay, so I think personally everything about KD trees is understandable from this one picture, so we need to try to get this. Basically, let's imagine we've got one-dimensional data. Okay, so the data points are these black dots, and Q here is our query point, and maybe some X star is our sort of candidate for the nearest neighbor. Okay. So what we're going to do is we're going to choose some value, some scalar value, in this case V, and this V is going to split the data into some things which are have these values which are less than V, these data points, and these other data points have values bigger than V. That's it. You're free to choose V, however you like, but one typical way to do it is something like close to the median of the data. Okay. So now let's say that after having done this partitioning of the data, so we know that, you come along with this query and you calculate the distance between this query and your current best. Okay. So this is this circle here. If this distance here is less than the distance between Q and V, there's no way that any of these data points here can be closer to Q than X star. It's a bit similar to what we had before, but it's not quite the same. I don't know if you see this, but now, what's the worst that could happen? Basically, it could be that, you know, in the gym, if you just compute this distance here, and I just give you Q, distance between Q and X star, you know, where could X star be in this geometric picture? You know, it could be basically anywhere, you know, in this on this circle in this case. Right? And the worst case in this particular scenario is that actually, you know, X star would be here as close as possible to the data over here. Right? So, but if this distance here is smaller than this distance from here to here, well, that's fine. Right? There's no way these guys can be possibly closer than this guy to there. There may be some other data point like this one, which is actually even closer. We don't know that yet. That's somewhere on the right-hand side. But we can at least eliminate all of these for consideration. Is it totally obvious? Yeah, it's totally obvious, isn't it? Right, good. Good, so all right. So that's our partition, left and right. So what we're going to do is say choose one dimension, first of all. Let's say dimension 1, axis 1, and we will choose a value of V, and we'll partition these data points into values, into points which have got value less than V. First dimension is to V, and bigger than, say, equal to V for the other one. So how do we generalize this to the multi-dimensional case? Well, we'll compute the squared Euclidean distance between Q and, say, our current best candidate, say, xi star. And so let's say, so xi is in the right. Okay, so let's just assume that. Well, that was a generality. So what is the square distance between, say, x and some query? And x now in this case is going to be in the left plane. This is corresponding to the one-dimensional situation we had before, where the current best is on the right and the remaining data points are on the left. And we want to know what the distance is between x and in the left plane and our query. Okay, so this is in the Euclidean case. Squared Euclidean case is given by this. The sum of the square distances between each individual dimension. And of course, because this is positive, this is necessarily bigger than this. Just taking one dimension. Right? It seems a pretty, terribly wasteful sort of expression, but there you go. And because this x1s here are always in the right-hand plane, okay, this means that we must have this situation is happening here. So yeah, so this is corresponding to the one-dimensional picture. Yeah, so this is the distance between q and v, q minus v squared, right? And that's bigger than q minus x star squared. So that's the corresponding situation. Okay. So in other words, if you know that this distance here is bigger than delta squared, your current best distance, then you know that this is bigger than delta squared, which means that your distance between any point in the left plane is bigger than the distance between your current best candidate and q in the right plane. Okay, so you could eliminate all those points to the left. On the other hand, if that's not true, if this is not bigger than that, there could be some point in the right-hand plane which is actually closer. Sorry, in the left-hand plane which should be closer. So, in other words, if this is true, you can get rid of the left-hand plane. If it's not true, then you have to consider the left-hand plane. There could be some point. Yeah, it's a bit hard to. You need to sit down and think about this stuff. But please do so. It's important. Okay, so.
Excuse me?
Yeah.
How would you find your best candidate?
But first of all, we're going to. Well, we'll come on to that actually, but we'll just choose one at random to start with.
Okay.
Well, I'll explain how that works in a minute. So there's a little bit more complicated stuff to do first. So the first thing is, how are we going to? So what I've just walked you through the steps. So we start off with the scalar case, okay? I now explained how it works for essentially data in multi-dimensions, but just for one. I only looked at one component of the vector so far. Right? I want to generalize this to looking at all components of the vector. And to do that, we're going to build a tree. Okay, and this is where we need to think about how to construct a tree. So what we're going to do, the KV tree itself, for n data points, consists of n nodes. And so each node corresponds to a data point. Okay, and that node will tell us what that data point is, and which points are to the left and which points are to the right for some given dimension. So we will define the data point, we'll define the dimension along which we're going to split the data, and it will tell us effectively, then we will know in some sense which data is to the left and which is to the right. Okay, so in order to construct this tree, we need to define some routine which will take as input a set of data points. So in this case, this would be a matrix where the first column would be, each column is a data point, and the axis is just it's just an index 1 through to d, which dimension you want to split the data along. Okay, and what we'll do is I call this routine, and it will then split this data into points which are to the left of some point, some points to the right of some point, and the point that we actually are splitting. To give you an example, here's one. So this is our two-dimensional data set X, and I call this routine split data in this case along dimension 1. So you look at the first line, right, in 259487, and basically you find, let's say, the median value here. What is it? Okay, it's 7 apparently. 2, 4, 5, 7, 8, 9. Okay, so roughly half is on the left and half is on the right of 7. Okay. So I then copy that vector down, and that 7, 2 is my mid data point. And the values on the left are, so in this case the x values are 2, 5 and 4 on the left, and the remaining ones go on the right. Okay, so what you do is you start with node 1 on the graph, on the tree. And in some sense, at the beginning, this node contains all of the data points. This is one way to actually, in a programming sense, to construct the tree. Okay. So we place all of the data in this node. We then call that split data routine, say along, say, dimension number 1. Okay, that will split the data into left and right, and it will also tell us the split point on the axis, right? So what we do then is we split that thing, we put half the left data in here, put the right data in here, we put here the mid data. We store also the fact that we split it along dimension 1. Okay? The data that was here then I don't need anymore, and I discard it. Okay, because the data is now being split into here and to here. Okay. So then you go down here and you do the same thing again. You've got a set of data points now. You call split data and you partition again into a left and right set. And then again you remove the data here and just replace it with this mid data point. Okay. And you do the same thing again, but in this case actually, for this particular problem, when you've done the split in this case, you're left with a single data point. So if there's a single data point, of course you don't need to split it anymore. So that you're done that branch. And similarly over here. And this case here, you when you split this point here, you also just get a single data point to the left and one midpoint. There's no right data in this case. The thing I should say is that what you do, each layer here in this binary tree is split by a different dimension. You don't have to do that, but you know, that's the conventional thing to do. So in this case, you've got 2 dimensions, so it's split by first dimension, say second dimension, first dimension, second dimension. You can just cycle through the dimensions as you're splitting. It's up to you really how you do that. It's up to you whether or not you choose the how to do the split data thing. It's just it's a choice.
So did you cycle through dimensions once, or can you continue cycling?
You cycle, keep going through it all the time. Yeah. So typically people they cycle through them. You don't even really, strictly speaking, have to do it. All that doesn't have to be split along as the same dimension as that in this level of this tree. You could have it any way that you like. Yeah. It's really, the mathematics works anyway. It's just, I think people over time, found that heuristic a reasonable one to do. It's just a function of the data, the way data tends to be distributed. Okay, so you get this binary tree here, right? And then at the end, we will have constructed this tree. So we've got now that these nodes contain a single data point, along with the axis along which it is split. Okay, so you can see that the storage cost is never going beyond n. We've got n data points to store. We're always staying around order n data points. So the storage cost is not too bad, and storing this tree is fine because we've just got, it's an n tree. So all you have to do is store, for each node, which is its parent. So that's linear n storage, linear times linear space storage as well. Okay, so what are the number of layers here? How many layers maximally can we have? Roughly speaking.
What now?
Yeah, because roughly speaking, we are partitioning the data into a left and a right half at each point. So we kind of, if you were to say do something like the the median value, you're splitting, half are going to be on the left and half are going to be on the right. So each point you're left with half of the data here as you'd had in the parent. So they're going to be log 2 of the number of data points maximally less in this procedure. Okay, so that means that the computational complexity you have to do, for each point here you have to. So half the data point went down here, then you have to do some, you call this with your split function again. So you have to do the median value, for example, it has to sort those data points. So you could do something more complex where you recognize that you've already done some sorting here and you kind of do something more fancy to do that. But basically you have to sort here, so at every layer you have to sort n data points in the naive implementation. So that means there are going to be log 2 of n, binary log of n, times by the number of data points. That's the time complexity of constructing a tree. So it's n log 2n. Okay. So this is what the nodes are. These are the data points in that particular example we had before. So 7, 2 went up there. I didn't write down the fact that that's split along dimension 1, but I'll just use the convention 1, 2, 1, 2 in this case. Data point number, whatever it was, node number 2 got this data point, node number 3 got that data point. Okay, that's our KD tree. So this is the visualization of it. Node number 1 is split along dimension 1, so that was value 7. Okay, so basically that means all children to the left of the branch of the root node basically have got values which are less than 7. X1 values less than 7. Okay, and then split number 2, we're splitting along the vertical dimension now, and that is here. So we're along 4. So, okay, so we do left and right. In this case, actually means up and down. And then 3 was also vertical, so 1, 2, 3, and then what's next one is 4 would be again this way. So the remaining splits are all this way. So in some sense, if you can think about is that this KD tree, in a way, is making a kind of partition of the space into hyper rectangles. Which I just kind of that's how I'm thinking about it. Okay, so what the heck can you do with this thing? Why is it useful? Well, if you really understood that one-dimensional case, you know everything. Okay, so you don't really need me to tell you how to do this, but I'll explain it anyway. Okay, you come along with the point. Let's say your query point is 9, 9, 2. So your query point is 9 and 2. So it's here. Okay. So the first thing we're going to do is we're going to rattle down through this KD tree to essentially this hypersphere, this hyperrectangle. Okay, how do I do that? Well, I come along with my point 9,2, and I say, well, look, I'm going to drop this 9,2 point at the top of the tree, and because I'm splitting along dimension 1 first, well, 9 is bigger than 7, so that means that this point 9,2 goes to the right. So I'll come to here. Okay. 9,2 is not equal to 9,6, so actually 9,2 is less than 6. So I go to the left. So I'm here. 2 is not equal to 8,1, so I'm stuck here. So this I end up in this part of the tree. Okay, so whatever data point is, you rattle down the tree to a leaf, splitting according to the dimensions. Okay. And now that you're here, you're going to start to traverse back, work your way back up the tree. It's a way to be defined. Okay, so that's the first stage, you rattle through to a leaf. And it's a complicated slide. Okay. So we need to go through this a little bit slowly. This is more complicated than it looks, I think. Oh no, it's more complicated. Yeah, it's not that complicated. Okay, so after writing down, so we've got the node number 6 on the tree on the extreme right, and that's our current guess as to the best nearest neighbour. So what we do is we compute the distance between Q, 9, 2, and that node number 6, which corresponded to point 8, 1. We calculate the squared Euclidean distance, and it's 9 minus 8 squared plus 2 minus 1 squared, which is 1 squared plus 1 squared, so it's 2. And we call that thing delta squared. That's the distance between our current best guess and Q is 2. Okay. So now you need to think about some other data points to consider. So we go to the next data point, which is going, you can get to that by going up the tree. It's parent to this point. Okay, so in this case, if you can, unfortunately, maybe you can keep on the screens the tree in front of you, but remember we were here. We're now going to go up, so we go up to here. And we consider that point. So we calculate its distance. So that's point 9, 6, is it? Yes. Okay, so this is 9 minus 9 squared plus 2 minus 6 squared, so that's 4 squared, 16. So that's bigger than delta squared, which is 2. So that's no good. That point is not closer to Q than node number 6. Okay, so we say that's not good. Now in this case, there are no children except this one we've already examined. Okay, so there's nowhere else to go except up. We need to get to another data point. Okay, so we're going to go up in this case to here, to 7, 2. Remember that this one now remains our best guess. Distance, square distance 2. Okay, so the top one is 0.72. That's got a distance, square distance 4. That's also worse than our best guess, which is 2. Okay, so now we're at the top. So there's nowhere else to go up, but in principle, all these points on the left we have to explore as well, the tree, right? Once we've explored all, because there are n data points or n nodes on this tree, then once we've explored every node on the tree, we're done, right? It's equivalent to have computed the distance between all points in the training set and Q. Now, let's have a look at this one. This is interesting here, right? So look at these children to the left. So we need to first of all understand whether or not any of those nodes in that left branch could possibly be closer than our current best point. So what we do know is that all those guys on the left, they've got x1 values less than 7. Right? Because we split it that way. So because if v, which in this case is 7, minus our query, first component in this case, which is 2, no, 9, sorry, yeah.
So it's at least 4.
It's at least 4, yeah. So it's got square distance at least 4. Okay, so that's bigger than our current best, which is 2. So that means whatever y values those guys have, they're only going to make it square distance bigger than 4. So that means you can forget about all those points on the left branch. Right. So that's good. So you basically, in this case, you're done. Right. So that's the general idea. So what you would do. Yeah, so just to remind you, we went here, we went to a leaf, in this case this one, we checked, found the nearest neighbour value, distance for that candidate, we went up, checking whether that would be nearest neighbour, etc. If that had been a nearer neighbour, then we would have set our delta squared to be that distance rather than, you know, we'd updated it basically. And then we keep working up, in this case, to the tree, top of the tree, and then in this case we could eliminate all of them down there. If on the other hand, so let's say we'd had a query, we'd ended up, say, I don't know, say here, right? We do the same thing, we calculate the delta square for that, we go up to here, and then we have to check now, you know, you could do, you calculate the distance for this one, this is another candidate. You know, if that's the closer distance, then that becomes a new delta squared. Then, depending on what the the distance between your delta squared and your q is, and this the mid value here, you can check whether or not you need to go and calculate this distance or not, whether or not this could be closer in exactly the same way as before. If it's not satisfying that, if it satisfies that bound, then you don't need to go and check this guy. You know it cannot be closer, and you'll work up your way up towards the tree again, to the root of the tree. Keep doing this kind of thing, you know. If it is not satisfying that bound, right, so you would actually have to go and examine this guy. If he's not closer, then that's fine, and you're done. Okay, so there's a kind of working your way, like a recursive algorithm required here to compute this. Sort of makes sense? So for those of you who like recursive programming, I'm sure you could do a very neat implementation. For those of you like me who don't like recursive programming, then you can try to do it in some other way. You can use the tree structures to do that. Just basically, in other words, just an adjacency matrix will tell you how to jump around this tree. Okay, so So let's have a look at this.
Is there a worse bound on how many things, like how many points you have to check?
Yeah, I mean, if you're unlucky, you may have to check all of them.
Oh, really? Oh, okay.
Yeah. Actually, I should have said that's the same with Orchard's algorithm. I think also with ESA as well. I mean, with Orchard's algorithm, it's clear to see because if you just had, if all the data points were in a line like that,
Yeah.
and you know your query, let's say your query point is here, okay, and your first guess as the best candidate was down here. Then what would happen in Orchard algorithm is you just keep working your way through all the data points. So it's unfortunately, in the worst case, it's doing no better than just searching through the data explicitly. And it's the same with ESA, and it's the same with this. In the worst case, it's also linear time. So yeah, we'll discuss a little bit about when you can expect these things to work reasonably well. So it's going to be. I don't know if this is a random report actually. That's slightly boring. It's almost the same.
We need something with more points.
Okay.
Something more dramatic.
More compelling. That's well made.
I suppose I was thinking sparse situations. You've got high dimensions and it's pretty sparse. It's going to make that.
It wouldn't really matter.
You would be checking because you have
You would have a lot of levels, yes. I guess you're right, actually.
You're going backwards. You'd basically be checking everything.
Yes, if the dimensions were much more than the number of your points.
Yeah.
Yeah.
this graphic is trying to explain, you know, the working its way through the tree. This little square. Maybe we can do this better with more data processing. Oops, that's a bit too much. I mean, this thing is very fast actually, but you know, my laptop is pretty helpless. This is one of the. This is like £100 this thing, so I don't recommend you use. Didn't plot. Yeah, sorry, I've not plotted. It seems going up to the parent at some points.
Okay.
It's a little bit one, isn't it? That's not good. The best X. There's a bug in this algorithm, actually, in my code. That's embarrassing. Okay, so I need to work on the code a little bit. But anyway, you get the kind of basic data. So I promise to debug it in some way. Okay, so there's small bugs in there. Okay, so all right, that's basically so there's two generic methods there. One is using metric triangle inequalities, okay, and the other one is using this sort of this sort of spatial data structure. And there are many other spatial data structures. There are tons of whole communities busy with this stuff. I'm not in it, but they like to do this stuff. They even have their own little workshops and stuff like that. And okay, so but the problem is that all of these methods that we've discussed so far, they kind of only work in special cases. Namely the case where the data is very dense. So you saw that in the low-dimensional case there, 2 dimensions, for example, you could eliminate a large number of the points automatically using the triangle inequality. And similarly, you'll find that using the KD tree in 2 dimensions with many points is efficient. Okay. In the worst case, it's bad, but in general, with a dense data in low dimensions, it's kind of fast. Now, what to think about a little bit in high dimensions, just imagine you take, say, data here in 2 dimensions, right, and you split it in each dimension, say, in half. So in this case, in 2 dimensions, you have 4 partitions. And in general, for a d-dimensional case, we'd have 2 to the power d, so the little partitions of this space, right? So if you want this kind of this situation that you saw intuitively, for example, with this 2-dimensional case, if we spread fairly uniformly over that 2D case, we could eliminate a lot of points, right? So what we want is a similar kind of idea that this data is sort of uniformly distributed in a high-dimensional case, right? But if we want sort of uniform distributions, we need at least like 1 data point per partition here. We're going to have 2 to the power d partitions, so that means that we need at least 2 to the power d data points to start having any sense of what uniform even really means, right? Otherwise, we're not going to get there. So, in general, though, if you got say 100 dimensions, 2 to the power d is astronomically big. It's absolutely huge. Right? There's no way you'd ever have that many data points. I don't know. It's probably bigger than the number of atoms in the universe or something crazy like that, right? So, what does that mean? Well, it means exponential, the vast majority of these partitions are completely empty. They don't contain any data points, right? So there's a tiny number of them, a fraction of them that contain data points. So this means it's totally non-uniform, right? So that's not good. And another way to think about this, so there's no way we're in that sort of uniform situation in high dimensions, typically. Let's think about this in another way. let's say that you have got, say, this unit 0, 1 hypercube, okay, in d dimensions. And we're going to sort of put a hypersphere inside this this hypercube. Okay, we're going to sort of see what fraction of the unit volume is contained by is made up of this volume of the hypersphere. Okay, so in d dimensions, the volume of a hypersphere is given by this formula here, for some radius. So if the radius is a half, you get that this fraction of the fraction of this, the occupancy of this compared to the whole volume is given by this expression here. So pi to the power d over 2 to the d over 2 factorial. And the point is that this d over 2 factorial here is huge. It's exponentially, it's super exponential. So it's basically giving you a really rapid drop in this fraction. So once you've gone up, just a few dimensions, this means that the fraction of the volume that this hypersphere occupies is very, very small. It shrinks very, very quickly, exponentially quickly, towards 0. So what does that mean? That means that if you think about it, the vast part of the space is actually in these corners of the hypercube. Okay. And how many corners are there? Well, there are 2 to the power d corners in a hypercube. So if your data is sort of, you have a finite number of data points, as we said before, they're not uniformly over all the partitions. Where are they? Well, effectively what it means for, in some sense, they are likely to be close to the hypercorners of this hypercube. Okay. And it's very unlikely they're going to be the same hypercorner. So there is a small number of the hypercorners are occupied, because there's an exponential number of them. So what that means typically is that 2 data points will be in different hypercorners of this hypercube. And you don't, there's no sense of, they're not necessarily really close by. So things tend to get kind of spread out in that sense. Okay, so the sense of, nearest neighbor or locality is kind of getting weaker as you go up with the dimensions. Things. I mean, this is kind of, yeah. I mean, this is for uniformly distributed data. So the situation may not be as disastrous in your particular example because the data is, real data is not uniformly distributed across the whole space. So it's not as bad as that. But these kind of discussions are interesting to bear in mind when we think about the reasons why maybe the nearest neighbor algorithms are these sort of speed-ups are not to be expected in such high-dimensional situations.
So in high dimensions, most distances will be equal.
Yeah, so they are the distribution. If you were to compute for, let's say you chose, say you had 1,000 data points, okay, and you, if you were to distribute those data points uniformly over your, say, however many dimensions you've got, you can compute the distances, you could compute all the distances between the data points. Right? And you could basically write down a histogram then of those distances. Right? So it would be, something like, you get some distances for distribution essentially of the distances between data points. As you increase the dimensionality, what will happen is that this distribution eventually becomes more compact. It tends to converge around sort of a single value in some sense. Not a single value, but it tends to get this compression effect. So they all start to, it goes up, the distances go higher in this case, but they're sort of, in some sense, their effective variance gets smaller. So if I were, to divide by some kind of length scale, it would effectively go towards 0. So so in other words, with uniformly distributed data, things start to all look the same distance apart, roughly speaking. So there's no like the idea, you know, of having a nearest neighbour starts to get very weak. Like all your neighbours are equally as far apart as any other. There's no single nearest neighbour. But like I said, in this situation is you have to bear in mind these theoretical considerations are for the uniformly distributed case. You know, people never, when they do these calculations, they never are talking about the way the actual data is distributed. You know, real data is very different from uniform distributed data. So I don't mean that you should say, oh, you know, this means that this argument is totally bogus. You just give up completely. That's not the case. But it's worth bearing in mind. You know, if things don't work well, you know, it's not clear that that the situation will work so well in high dimensions. And you'll typically find that if you were to take this code and you run it, for example, the Orchard or the ESA code, and you run it, just increase the dimensionality, you'll see that the number of distance calculations that we require to do actually increases as we increase the dimension. So you know the advantage starts to go down. But that's again, you know, because in that particular demo is I'm distributing the data uniformly and, across the space, so it's kind of tying in with this theoretical picture. But it would be more interesting to do with a real example, and some of the papers, you know, they discuss that. But certainly, I mean, the people who do things like, you know, KD trees and stuff, if you work at, you know, Google or wherever, you're busy with this stuff all the time. This is it's a big thing, basically. So Andrew Moore, who was one of the first guys to write about KD trees in the machine learning community, he works on this stuff full time at Google. So, and similar, you know, extensions. Okay, that's it for nearest neighbour. Sorry about the bug in the KD tree. I'll fix it for next time. So we're going to have a 20-minute break, and as usual, one of you will come and present to